We're going to move into talking about surfaces, and eventually we'll be integrating a vector field over a surface. But first we have to talk about some different ways to express a surface. So let's go back to something that we saw in Math 126, which was the parameterization of a curve. So something like this, t cosine t sine t, for example. This is one that we've kind of seen recently. This is a helix. And basically you can have any functions of t in for x, y, and z, and that's going to draw some sort of curve. That's not this curve, but some sort of curve in three-dimensional space. In particular, here's an easy one. This is a line. And remember, this was a line passing through the origin with direction vector 1, 2, 3. So we could walk as many units as we wanted, t units in the direction 1, 2, 3. Okay, so notice that there's one parameter in these curves, and that gives us a curve, which has dimension 1. And if you've taken linear algebra, you kind of know the concept of a free variable. So the number of parameters gives you the number of dimensions of the thing. So what if we increase the number of parameters? What if we took this line and then we changed it to t, 2t, 3t. Let's just add like a second parameter, t plus u. What happens here? This still passes through the origin, right? If t equals 0 and u equals 0, then we still get the vector 0, 0, 0. So still passes through the origin. We can still put in any value of t and walk in the direction 1, 2, 3. The only new thing is now I can mess it up in the x-coordinate. So I can also walk in the direction. So now I have two directions. I can still walk in the direction 1, 2, 3, but now I can also walk in the direction 1, 0, 0, and that's due to the u. And so what this does, and I can walk in some combination of the two directions as well. I can walk first in one and then in the other. So what this gives us is a plane. It's a plane passing through the origin and containing those two direction vectors. The vectors 1, 2, 3, and 1, 0, 0. And that completely describes the plane. So notice here, before we had one parameter, and it gave us a curve which was one-dimensional. Now we have two parameters, which gives us a surface which has two dimensions. We say dimension 2. So the number of parameters always gives us the number of dimensions. If I added three parameters, I'm going to argue that I could get more or less. It depends. If I added a third parameter just in the x-coordinate, I couldn't do it. But so I couldn't do t plus u plus v, comma 2t, comma 3t. I couldn't get anywhere in 3 space there. That's a weird adding of a third parameter. So there's some things that aren't allowed, but basically, if I have 3 parameters, if I did it this way, I could certainly do it. This can get me any point in R3. So dimension is a little bit weird. It doesn't always work this way, that the number of parameters gives me the number of dimensions. I can do things where it doesn't. I can even do things back here where it doesn't work. Actually, here's one where it doesn't work. If I did t, let's see, t plus u, 2t plus 2u, 3t plus 3u, then no matter what I put in for t and u, my y-coordinate is always double my x-coordinate, and my z-coordinate is always triple my x-coordinate. So that's a problem, because then that just gets us back to the original line that we had without the u. So that's not interesting. Okay, so sometimes it screws up and the parameter doesn't give us the number of dimensions. But if we don't try to make a special thing, usually this will happen. So usually if I have 3 parameters, I can get any point in R3. And here's a really, really simple example of that. If I just have x, comma y, comma z, right? That's a general point in R3. This is actually an object with 3 parameters. So 3 parameters gives me space, which is 3 dimensions, dimension 3. And if you think of linear algebra, that's 3 free variables. So that's kind of cool. We can also talk about this backwards. If you were there for, or if you tried quiz, I believe it was quiz 2, problem 7 and 8. I had a little discussion in the Zoom session about how, like, if you have something like z equals x squared plus y squared, that's a surface. And we kind of recognize, so this is a paraboloid, but it doesn't matter. You don't have to name the surface. If it's one equation with x, y, and z all in the same equation, that generally describes a surface. It doesn't have to describe a surface, but it generally does. Okay, and this is 2 dimensions. And this is one equation. One equation describing 2 dimensions. What if I wanted to describe a curve with equations? So notice before I described a curve parametrically, with kind of a vector with a parameter in it. Could I describe a curve with equations? I could. I could describe it as an intersection of 2 surfaces. If I did z equals x squared plus y squared, intersected with z equals 3, say. What's a picture of that? That's a paraboloid intersected with x, y, z. Here's 3, so we're intersecting the paraboloid with that plane, and now that the thing that I'm describing with that system of equations is this circle. So here is a curve, which is in 1 dimension, described by 2 equations. So here's a general rule. Again, there are special cases where this isn't always true. For example, like, here's a silly one. What if my second curve was 2z equals 2x squared plus 2y squared? I've tried to make it look different, but this is really the same surface as the original. So now the intersection of the 2 things is a surface and not a curve. So now we have the wrong number of dimensions. But a kind of general rule is number of equations, for the most part, plus number of dimensions of the thing you're describing. So over here, 1 equation described a surface. Over here, 2 equations described a curve, equals number of dimensions in the ambient space. Or basically, number of variables that might show up in the equations. So here, there's 3 variables that show up in the equation. So we're graphing in 3-dimensional space. We have 2 equations, not this one, but the original one, z equals 3. So we end up with a 1-dimensional thing, a curve. Here we had 3 variables in ambient space. We're graphing in 3-dimensional space, 1 equation. That's like one, if you think about the optimization problems in Math 126, 1 equation, kind of like 1 constraint. So we're knocking the space down by a dimension. We end up in 2 dimensions. Here we have 2 constraints. Z has to equal x squared plus y squared, and z has to equal 3. We're knocking the space down with every equation by a dimension, so we end up with only 1 dimension. If you had 3 equations, you'd end up with a 0-dimensional thing. What is a 0-dimensional thing? 0 dimensions is either, it's a set of points. It could be empty. Set of points. So let's add a 3rd dimension to this. we have z equals x squared plus y squared, z equals 3, and let's say x equals 0. So what's x equals 0? That's this plane. It goes here and up, right? So then the set of points is those 2 points on the circle that are also in the xz plane. But if I had put instead x equals 1,000, now I'm in a plane all the way over here. It doesn't intersect the circle, so now I don't have any points. So that's where the set of points can be empty. So that's just something to think about in the background as we talk about surfaces and why surfaces basically shows us any surface with 2 parameters, or any vector with 2 parameters gives us a surface, if that's the right number of dimensions.